What if every choice you've ever made could be rewritten with a single trip through time? Imagine stepping into a machine, pressing a button, and suddenly finding yourself face to face with a younger version of you. Would you warn them, guide them, or simply watch as history unfolds? Time travel isn't just the stuff of science fiction. It's a concept that has puzzled scientists, philosophers, and dreamers for centuries. Today, we're diving into 25 mind-bending theories about time travel that will challenge everything you think you know about reality. From paradoxes that twist logic to the mind-blowing possibilities of alternate universes, these theories don't just spark curiosity, they ignite a fire in our understanding of the cosmos. So, buckle up, because by the end of this journey, you might just question whether time is as linear as it seems. Let's begin. Now, turning to the first of our mind-bending theories, we encounter the grandfather paradox, a classic time travel dilemma that has puzzled thinkers for decades. Imagine this: you travel back in time and accidentally or intentionally prevent your grandfather from meeting your grandmother. If they never meet, your parent is never born, and neither are you. But if you were never born, how could you have traveled back in time to interfere in the first place? This paradox creates a logical loop that seems impossible to resolve. It challenges the very idea of cause and effect, forcing us to question whether time travel could ever be possible without unraveling the fabric of reality. Philosophers and scientists have proposed several solutions to this paradox. One popular idea is the concept of parallel universes, where every decision creates a new timeline. In this scenario, if you prevent your grandparents from meeting, you wouldn't erase yourself from existence. You'd simply create a new timeline where you never existed, while your original timeline remains untouched. Another solution is the idea of self-correcting timelines, where the universe somehow prevents paradoxes from occurring. For example, no matter how hard you try, you might find it impossible to alter key events in the past, ensuring that history remains consistent. The grandfather paradox isn't just a thought experiment, it's a gateway to deeper questions about free will, destiny, and the nature of time itself. Could the universe have built-in safeguards to prevent paradoxes, or are we bound by the laws of causality, unable to change the past no matter how hard we try? As we explore these questions, one thing becomes clear: time travel, if it's ever possible, would come with rules and consequences that defy our everyday understanding of reality. And with that, we move forward to our next theory, where the mysteries of time travel only deepen. Now, turning to our next mind-bending theory, we encounter the Bootstrap Paradox, a concept that twists our understanding of cause and effect into an infinite loop. Imagine this: you find a book in your possession, a masterpiece that inspires you to become a writer. Years later, you travel back in time and give that same book to your younger self. But here's the catch: where did the book originally come from? It wasn't written by anyone, it simply exists in a loop with no clear origin. This is the essence of the Bootstrap Paradox, where an object or piece of information seems to have no beginning, trapped in a cycle that defies logic. This paradox challenges the very foundation of causality, the idea that every effect must have a cause. In the case of the book, it appears to create itself, raising questions about the nature of existence and reality. How can something exist without a starting point? And if time travel allows for such loops, what does that mean for our understanding of the universe? Some theorists suggest that the Bootstrap Paradox implies a universe where certain events or objects are self-sustaining, existing outside the normal flow of cause and effect. Others argue that it points to a deeper, perhaps even unknowable, structure of reality where the rules we take for granted no longer apply. The Bootstrap Paradox isn't just a fascinating thought experiment, it's a profound challenge to our understanding of time, existence, and the very fabric of the universe. It forces us to consider whether some things might exist beyond the boundaries of logic, or if our perception of cause and effect is simply too limited to grasp the true nature of time travel. As we delve deeper into these mysteries, one thing is certain: the Bootstrap Paradox leaves us with more questions than answers, and the journey through the enigmas of time travel is far from over. Now turning to our next theory, we explore the many worlds interpretation, a fascinating idea from the realm of quantum mechanics that reshapes how we think about time, choices, and reality itself. Imagine this: every decision you make, no matter how small, doesn't just lead to one outcome, it creates an entirely new universe. That's right, every time you choose between coffee or tea, take a left turn instead of a right, or even decide to stay home instead of going out, a new branch of reality splits off, forming a parallel universe where the other choice was made. This means there are countless versions of you, living out every possible outcome of every decision you've ever faced. So, how does this relate to time travel? Well, if the many worlds interpretation is correct, traveling back in time wouldn't create paradoxes like the ones we've discussed earlier. Instead, a time traveler would simply shift into an alternate timeline, one where their actions create a new branch of reality. For example, if you went back in time and prevented a historical event, you wouldn't be altering your own timeline. You'd be stepping into a new one where that event never happened. This means the original timeline remains untouched, and the paradoxes we fear, like the grandfather paradox or the bootstrap paradox, simply wouldn't apply. But this theory doesn't just solve the problem of paradoxes, it also raises profound questions about free will and the nature of reality. If every possible decision creates a new universe, does that mean our choices are predetermined, or do we truly have the power to shape our own paths? And if there are infinite versions of us living out every possible life, what does that say about the uniqueness of our existence? The many worlds interpretation challenges us to rethink not just time travel, but the very fabric of who we are and how we fit into the cosmos. As we ponder these questions, one thing becomes clear: the many worlds interpretation offers a bold and intriguing perspective on time travel, one that opens up endless possibilities while leaving us with even more to explore. With this theory in mind, let's continue our journey through the mysteries of time and space, where every twist and turn reveals new layers of wonder and complexity. Now turning to our next theory, we delve into the intriguing concept of closed time-like curves, a fascinating idea rooted in the framework of general relativity. Imagine a loop in spacetime where time itself bends back on itself, creating a path that could, in theory, allow for time travel. These loops, known as closed time-like curves, suggest that under certain conditions, it might be possible to travel back to a point in time without violating the laws of physics as we understand them. So, how do these curves work? According to Einstein's theory of general relativity, massive objects like black holes can warp spacetime so dramatically that they create these loops. Picture spacetime as a fabric. When an object with immense mass, like a black hole, sits on that fabric, it creates a deep curve. In some extreme scenarios, this curve could loop back on itself, forming a closed time-like curve. If you were to follow this curve, you might find yourself returning to a moment in your own past, effectively traveling through time. But while the idea is thrilling, it's not without its challenges. For one, the conditions required to create a closed time-like curve are so extreme that they're nearly impossible to replicate or observe in our universe. The immense gravitational forces needed to bend spacetime in this way are typically found only around objects like black holes, where the environment is so hostile that survival, let alone time travel, seems impossible. Additionally, the existence of these curves raises questions about causality. If you could travel back in time and interact with your past self, what would that mean for the flow of cause and effect? Could you create a paradox, or would the universe find a way to prevent it? Despite these challenges, closed time-like curves remain a captivating area of study for physicists and science fiction enthusiasts alike. They push the boundaries of our understanding of time, space, and the fundamental laws that govern our universe. As we continue to explore the mysteries of time travel, these curves remind us that the cosmos is full of surprises waiting to be uncovered. With this theory in mind, let's move forward to the next chapter of our journey, where even more mind-bending ideas await. Now turning to our next theory, we explore the fascinating concept of wormholes as potential time machines. Often referred to as Einstein-Rosen bridges, wormholes are theoretical passages through spacetime that could create shortcuts for long journeys across the universe, or even through time itself. Imagine folding a piece of paper so that two distant points touch. A wormhole would be like poking a hole through that fold, allowing you to travel instantly from one point to another. But how exactly could these cosmic tunnels enable time travel? According to the equations of general relativity, wormholes are possible, but they come with a catch. For a wormhole to be traversable, it would need to be stabilized by something known as exotic matter, a substance with negative energy density that counteracts the natural tendency of the wormhole to collapse. This exotic matter is purely theoretical, and we have yet to discover anything like it in the universe. Even if it exists, the amount of energy required to create and maintain a stable wormhole would be astronomical, far beyond anything humanity could currently achieve. But let's suppose for a moment that we could overcome these challenges. If a wormhole were stabilized, it could theoretically connect not just 2 points in space, but also 2 points in time. For example, one end of the wormhole could be placed near a massive object like a black hole, where time slows down due to intense gravity, while the other end remains in a region where time flows normally. This difference in the flow of time between the two ends could create a bridge through which you could travel to the past or future. However, the implications of such a discovery are as mind-bending as they are complex. If wormholes could be used for time travel, they would raise profound questions about causality and the nature of reality. Could you travel back in time and change the course of history? Or would the universe enforce some form of cosmic rule to prevent paradoxes? These questions remain unanswered, but they highlight the incredible potential and challenges of wormholes as time machines. As we continue our journey through the mysteries of time travel, wormholes remind us that the universe is full of possibilities that stretch the limits of our imagination. With this theory in mind, let's move forward to the next chapter, where even more astonishing ideas await. Now turning to our next theory, we delve into the intriguing phenomenon of time dilation, a cornerstone of Einstein's theory of relativity. This theory fundamentally changed our understanding of time, revealing that it is not a constant, unchanging force, but rather something that can stretch and bend depending on speed and gravity. Imagine time as a river. Sometimes it flows quickly and other times it slows to a trickle, depending on where you are and how fast you're moving. One of the most fascinating aspects of time dilation is how it affects objects near massive gravitational fields or traveling at incredibly high speeds. For instance, astronauts aboard the International Space Station experience time slightly differently than those of us on Earth, because they are moving at high speeds and are farther from Earth's gravitational pull. Time for them passes just a tiny bit slower. Over the course of a 6-month mission, this difference might only amount to a few milliseconds, but it's a real-world example of how time can be manipulated. To put it simply, the faster you move or the closer you are to a massive object like a black hole, the slower time passes for you compared to someone in a less extreme environment. This means that if you were to orbit a black hole for a few hours, years could pass for people back on Earth. In a sense, this is a form of time travel into the future. You're not traveling backward, but you're skipping ahead relative to others. Einstein's theory of relativity also explains why this happens. Massive objects like planets and stars warp the fabric of spacetime, creating what we perceive as gravity. The stronger the gravitational field, the more spacetime is curved and the slower time moves. Similarly, as you approach the speed of light, time slows down for you compared to someone standing still. This has been confirmed through experiments with atomic clocks, which show that time indeed ticks slower at high speeds or in strong gravitational fields. But what does this mean for time travel? While we can't yet build a machine to take us close to the speed of light or near a black hole, the principles of time dilation suggest that such feats could one day allow us to leap into the future. Imagine a spacecraft traveling at near light speed. Its passengers might age only a few years while centuries pass on Earth. This isn't just science fiction, it's a real possibility grounded in the laws of physics. As we continue to explore the mysteries of time travel, time dilation reminds us that the universe operates in ways that often defy our everyday experiences. With this theory in mind, let's move forward to the next chapter, where even more astonishing ideas await. Now turning to our next theory, we explore the Novikov Self-Consistency Principle, a fascinating idea that offers a solution to one of the biggest headaches in time travel paradoxes. This principle suggests that any actions taken by a time traveler were always meant to happen, meaning they are already part of history. In other words, the universe has a built-in mechanism to prevent contradictions, ensuring that events remain consistent no matter what. Imagine you travel back in time to prevent a historical event, like stopping a famous inventor from creating a groundbreaking invention. According to the Novikov Self-Consistency Principle, your attempt would fail not because of bad luck, but because the universe would conspire to make sure the invention still happens. Maybe you accidentally inspire the inventor instead, or perhaps your interference leads to the exact outcome you are trying to prevent. The point is, the timeline remains intact and paradoxes are avoided. This principle enforces a deterministic view of the universe, where everything is predetermined and free will is an illusion. If the Novikov principle holds true, then every action you take as a time traveler was always part of the timeline, and you are never truly free to change it. This raises profound questions about the nature of choice and whether we have any real control over our lives. Are we just following a script written by the universe, or is there room for genuine freedom? The implications of this theory are both comforting and unsettling. On one hand, it eliminates the fear of creating paradoxes, like the infamous grandfather paradox, where you might accidentally prevent your own existence. On the other hand, it challenges our sense of agency, suggesting that even time travelers are bound by the unbreakable rules of causality. As we continue to unravel the mysteries of time travel, the Novikov Self-Consistency Principle reminds us that the universe might have its own way of keeping things in order. With this thought-provoking theory in mind, let's move forward to the next chapter, where even more mind-bending ideas await. Now turning to our next theory, we delve into the block universe theory, a concept that completely redefines how we perceive time. Unlike the traditional view of time as a linear progression from past to present to future, the block universe theory suggests that past, present, and future all exist simultaneously. Imagine the universe as a four-dimensional block, where every moment in time, every event, every decision, every outcome is fixed in place like frames in a film reel. In this model, time doesn't flow, it simply is. This idea challenges our everyday experience of time as something that moves forward. Instead, it proposes that what we call the present is just a slice of this eternal block, and our perception of time passing is merely an illusion. From this perspective, the past isn't gone, and the future isn't unwritten. They're both just as real as the present, existing in different parts of the block. So, what does this mean for time travel? If the block universe theory is correct, traveling through time wouldn't involve changing the past or altering the future. Instead, it would mean navigating to a different part of the block where events are already set in stone. This eliminates the possibility of paradoxes like the grandfather paradox, because everything that happens or will happen is already part of the block. This theory also raises profound questions about free will. If the future is already out there, waiting for us to experience it, do we truly have the power to make choices? Or are our decisions predetermined, with the illusion of choice being just another layer of the block? The block universe theory forces us to rethink not only time travel but also our place in the universe. It suggests that our lives are part of a vast, unchanging tapestry where every moment is eternally present. As we continue to explore the mysteries of time, this theory offers a radical yet compelling perspective on the nature of reality itself. With this in mind, let's move forward to the next chapter where even more astonishing theories await. Now turning to our next theory, we explore the fascinating concept of time crystals, a groundbreaking discovery that challenges our understanding of matter and time itself. Unlike ordinary crystals, which have repeating patterns in space, time crystals exhibit a unique property: they repeat their structure in time. This means that, without any external energy input, time crystals oscillate between states in a predictable, periodic manner, defying the traditional laws of thermodynamics. First proposed in 2012 by Nobel laureate Frank Wilczek, time crystals were initially met with skepticism. However, in 2017, researchers successfully created them in laboratory settings, confirming their existence. These crystals are not just a scientific curiosity, they represent an entirely new phase of matter, one that operates outside the bounds of conventional physics. So how do time crystals work? Imagine a clock that ticks endlessly without needing to be wound. Time crystals achieve a similar effect, cycling through their states in a loop that persists indefinitely. This behavior is made possible by a phenomenon called time symmetry breaking, where the crystal's structure remains stable despite the passage of time. The implications of time crystals are profound, particularly in the field of quantum computing. Their ability to maintain coherence over time could revolutionize how we store and process quantum information, potentially leading to more stable and efficient quantum systems. Additionally, time crystals might offer new insights into the nature of time itself, providing clues about how time could be manipulated or even controlled. While the practical applications of time crystals are still in their infancy, their discovery opens up exciting possibilities for both science and technology. By studying these strange, time-repeating structures, we may uncover deeper truths about the universe and our place within it. As we continue to unravel the mysteries of time, time crystals stand as a testament to the boundless potential of human curiosity and innovation. With this in mind, let's move forward to the next chapter where even more astonishing theories await. Now turning to our next theory, we delve into the intriguing concept of the Alcubierre Drive, a theoretical warp drive that could revolutionize space travel as we know it. Proposed by physicist Miguel Alcubierre in 1994, this idea suggests a way to achieve faster-than-light travel without violating Einstein's theory of relativity. Instead of moving through space, the Alcubierre Drive would manipulate spacetime itself, creating a warp bubble around a spacecraft. Here's how it works. The drive would contract spacetime in front of the ship while expanding it behind, effectively allowing the vessel to ride a wave of distorted spacetime. This means the ship itself wouldn't be moving faster than light within the bubble, but the bubble itself could traverse vast distances at incredible speeds. It's like surfing on a cosmic wave where the fabric of the universe does the heavy lifting. However, the Alcubierre Drive isn't without its challenges. One of the biggest hurdles is the enormous amount of energy required to create and sustain the warp bubble. Early calculations suggested the energy needed would be equivalent to the mass of an entire planet. While more recent studies have proposed ways to reduce this requirement, the technology to harness such energy remains far beyond our current capabilities. Another concern is the potential for catastrophic effects on the regions of spacetime being manipulated. The creation of a warp bubble could generate intense gravitational waves or even exotic particles, raising questions about the safety and feasibility of such a journey. Despite these challenges, the Alcubierre Drive holds tantalizing possibilities for time travel. By bending spacetime, the drive could theoretically create closed time-like curves, allowing for travel into the past or future. Imagine a future where humanity could explore distant galaxies or revisit historical events, all within a single lifetime. While the Alcubierre Drive remains a theoretical concept, it serves as a powerful reminder of the boundless potential of human ingenuity. As we continue to push the boundaries of physics and engineering, who knows what breakthroughs await? With this in mind, let's move forward to the next chapter, where even more astonishing theories await. Now turning to our next theory, we explore the fascinating concept of the Tipler cylinder, a theoretical device that could potentially enable time travel. Proposed by physicist Frank Tipler in 1974, this idea revolves around a massive, infinitely long cylinder rotating at an incredibly high speed. The rotation of such a cylinder would warp spacetime around it, creating what are known as closed time-like curves. These curves would allow an object or person to travel back in time by following a path that loops back on itself within the fabric of spacetime. The Tipler cylinder works by generating a gravitational field so intense that it twists spacetime into a helical shape. If you were to travel around the cylinder in the direction of its rotation, you could theoretically return to your starting point in both space and time. This means you could revisit moments in your own past, creating a loop where cause and effect become intertwined. However, building a Tipler cylinder presents significant challenges. First, the cylinder would need to be infinitely long, which is impossible with our current understanding of physics and engineering. Even if we could create a finite version, the energy required to spin such a massive object at the necessary speeds would be beyond anything humanity has ever produced. Additionally, the cylinder would need to be made of an exotic material with negative energy density to stabilize the spacetime distortions, something we have yet to discover or create. Another major concern is the potential for paradoxes. If time travel were possible using a Tipler cylinder, it could lead to situations where the past is altered in ways that contradict the present. For example, what if someone traveled back in time and prevented their own birth? These paradoxes challenge our understanding of causality and raise questions about the feasibility of such a device. Despite these obstacles, the Tipler cylinder remains a compelling idea in the realm of theoretical physics. It pushes us to think about the nature of spacetime, gravity, and the limits of human ingenuity. While we may never build a Tipler cylinder, the concept inspires us to imagine a future where the boundaries of time and space are no longer fixed. With this in mind, let's move forward to the next chapter, where even more astonishing theories await. Now turning to our next theory, we delve into the intriguing concept of the chronology protection conjecture, proposed by the legendary physicist Stephen Hawking. This idea suggests that the laws of physics inherently prevent time travel to the past, acting as a kind of cosmic safeguard to protect the timeline from paradoxes and inconsistencies. Hawking famously argued that if time travel to the past were possible, we would have already encountered tourists from the future. Since we haven't, he concluded that nature must have a way of preventing such journeys. The chronology protection conjecture is deeply rooted in the principles of quantum mechanics and general relativity. In the quantum realm, particles and energy behave in ways that defy classical physics, often leading to unpredictable outcomes. Hawking proposed that these quantum effects could create a kind of feedback loop when attempting to travel back in time. For example, if a particle were to loop back into its own past, the resulting interactions could generate infinite energy, effectively making time travel impossible. General relativity, on the other hand, allows for the theoretical existence of closed time-like curves, as we've seen in previous theories like the Tipler cylinder. However, Hawking suggested that these curves might be unstable or impossible to sustain in reality. He argued that any attempt to create a closed time-like curve would trigger quantum effects that would disrupt the spacetime fabric, preventing the curve from forming in the first place. Despite its compelling logic, the chronology protection conjecture remains unproven. While it offers a plausible explanation for why we haven't observed time travelers, it doesn't provide a definitive mechanism for how nature enforces this protection. Some physicists argue that the conjecture is more of a philosophical stance than a scientific theory, as it relies on assumptions about the behavior of the universe that we can't yet test or observe. Nevertheless, the idea challenges us to think deeply about the nature of time and causality. If the universe truly has a built-in mechanism to prevent time travel, what does that say about the flow of time itself? Is time a fixed one-way street, or is it more flexible than we realize? These questions push the boundaries of our understanding and keep the mystery of time travel alive. With this in mind, let's move forward to the next chapter, where even more astonishing theories await. Now turning to our next theory, we explore the fascinating concept of the multiverse and how it could revolutionize our understanding of time travel. Imagine a reality where every decision you make creates a new universe, each one branching off into its own unique timeline. This is the core idea behind the multiverse theory, and it offers a compelling solution to the paradoxes that plague traditional time travel narratives. In a multiverse, time travel wouldn't require altering the past of your own universe. Instead, you could journey to a parallel universe where history unfolds differently. For example, if you traveled back in time to prevent a historical event, you wouldn't be changing your own timeline, you'd simply be entering a new one where that event never occurred. This means the grandfather paradox, where you might prevent your own existence, becomes irrelevant. In the multiverse framework, your original timeline remains untouched, while the new one branches off with its own set of consequences. But how would travelers navigate between these infinite universes? Some theories suggest that quantum mechanics could hold the key. Quantum particles are known to exist in multiple states simultaneously, a phenomenon called superposition. If we could harness this principle, it might be possible to create a bridge between universes, allowing travelers to shift from one timeline to another. However, the energy requirements and technological challenges for such a feat are beyond our current understanding. The idea of branching timelines also raises intriguing questions about free will and destiny. If every decision creates a new universe, does that mean all possible outcomes already exist somewhere in the multiverse? And if so, does our sense of choice truly matter, or are we simply following a predetermined path in our own timeline? These questions blur the line between science and philosophy, challenging us to rethink the nature of reality itself. While the multiverse theory offers a tantalizing escape from the paradoxes of time travel, it remains largely speculative. Scientists have yet to find concrete evidence of parallel universes, and the mechanisms for traveling between them are purely theoretical. Still, the concept inspires endless possibilities, from exploring alternate histories to discovering worlds where the laws of physics are entirely different. As we continue our journey through these mind-bending theories, the multiverse reminds us that the universe, or universes, may be far stranger and more complex than we ever imagined. With this in mind, let's move forward to the next chapter, where even more astonishing ideas await. Now turning to our next theory, we delve into the mysterious world of quantum entanglement and its potential connection to time travel. Quantum entanglement is a phenomenon where two particles become linked, no matter how far apart they are in space. What's truly mind-bending is that changes to one particle instantly affect the other, even if they're light years apart. This strange behavior has led scientists to wonder, could entanglement also allow information to travel backward in time? Imagine two entangled particles, one here on Earth and the other on a distant planet. If we manipulate the particle on Earth, its entangled partner instantly reflects that change, seemingly defying the speed of light. Some researchers have proposed that this instantaneous connection might not just cross space, it could also bridge time. In theory, if we could control entanglement precisely, we might be able to send information backward in time, effectively creating a form of time travel for data. Experiments have already hinted at this possibility. In one groundbreaking study, scientists observed that entangled particles appeared to influence each other's states even when measurements were made in a specific sequence that seemed to reverse the usual flow of time. While this doesn't mean we're sending messages to the past just yet, it does suggest that the relationship between entanglement and time is far more complex than we once thought. But how could this work in practice? One idea is that entangled particles could act as a kind of time bridge, allowing information to flow backward through the quantum realm. For example, if we encoded a message into an entangled particle, its partner might reflect that message at an earlier point in time. While this remains speculative, it opens up fascinating possibilities for communication across time, potentially revolutionizing fields like cryptography and computing. Of course, the challenges are immense. Harnessing quantum entanglement for time travel would require technology far beyond our current capabilities, not to mention a deeper understanding of the quantum world itself. Yet, the very idea that particles can influence each other across time and space pushes the boundaries of what we thought was possible, blurring the lines between science fiction and reality. As we continue to explore these mind-bending theories, quantum entanglement reminds us that the universe operates on rules that defy our everyday intuition. With this in mind, let's move forward to the next chapter where even more astonishing ideas await. Now turning to our next theory, we explore the fascinating concept of the holographic principle, a revolutionary idea that suggests our universe might be a hologram. At first glance, this might sound like something out of science fiction, but it's a serious scientific theory that could fundamentally change how we understand time, space, and reality itself. The holographic principle proposes that all the information in a volume of space can be thought of as encoded on a boundary to that space, much like a hologram encodes a three-dimensional image on a two-dimensional surface. In simpler terms, it suggests that the universe we perceive, with its three dimensions of space and one of time, might actually be a projection from a two-dimensional surface at its boundary. This idea challenges our traditional understanding of reality, implying that everything we see and experience could be a kind of cosmic illusion. So, what does this mean for time travel? If the universe is a hologram, then time itself might not be as linear or fixed as we think. Instead, it could be a construct emerging from the interactions of information on this two-dimensional surface. This opens up the possibility that time travel might not involve moving through a physical timeline, but rather manipulating the underlying information that creates our perception of time. Imagine being able to rewrite the holographic code of the universe, effectively altering the past or future. The implications of the holographic principle are profound. It suggests that time and space are not fundamental aspects of reality, but rather emergent properties of a deeper, more fundamental layer of existence. This could mean that the barriers to time travel, like causality and the speed of light, might not be as insurmountable as they seem. Instead, they could be features of the holographic projection, which might be bypassed or altered if we can understand and manipulate the underlying code. While this theory is still in its early stages, it has already sparked exciting debates and experiments. Scientists are exploring how the holographic principle might reconcile the seemingly incompatible laws of quantum mechanics and general relativity, potentially leading to a unified theory of physics. If proven, it could not only redefine our understanding of time travel, but also transform our perception of reality itself. As we continue to unravel the mysteries of the universe, the holographic principle reminds us that reality might be far stranger and more interconnected than we ever imagined. With this in mind, let's move forward to the next chapter where even more astonishing ideas await. Now turning to our next theory, we delve into the intriguing concept of eternalism, a philosophical perspective that challenges our everyday understanding of time. Eternalism proposes that past, present, and future are equally real, existing simultaneously in a vast, unchanging block of space-time. Unlike the common view that only the present moment is real, eternalism suggests that time is more like a landscape where every moment, whether it's the birth of the universe or the distant future, exists eternally. This idea aligns closely with the block universe theory, which we touched on earlier. In the block universe, time is not a flowing river but a static, four-dimensional structure where all events are fixed in place. Think of it like a movie reel. Every frame exists, but we experience it one frame at a time. Eternalism takes this a step further by asserting that all these frames are equally real, even if we can only perceive one at a time. So, what does this mean for time travel? If all moments in time are equally real, then traveling to the past or future wouldn't involve changing anything. It would simply mean moving to a different part of the block universe. This view eliminates many of the paradoxes associated with time travel, such as the grandfather paradox, because the past and future are already set in stone. You couldn't change the past because it's just as real and unchangeable as the present. Instead, any actions you take while time traveling would have always been part of the timeline. Eternalism also raises fascinating questions about free will and destiny. If the future is already out there, waiting to be experienced, does that mean our choices are predetermined? Or do our decisions still shape the future, even if that future is already part of the block universe? These questions remain at the heart of philosophical debates, blending science with deep existential inquiry. While eternalism might seem abstract, it offers a compelling framework for understanding time travel. It suggests that the universe is a vast, interconnected tapestry where every moment is woven into the fabric of reality. Whether or not we ever achieve time travel, eternalism reminds us that the past, present, and future are all part of the same grand story, a story that we are still learning to read. With this perspective in mind, let's move forward to the next theory, where we'll explore another fascinating idea that challenges our understanding of time and reality. Now turning to our next theory, we explore the predestination paradox, a mind-bending concept that suggests time travelers' actions are not only inevitable but also essential to maintaining the timeline. Imagine this: you travel back in time to ensure a specific event happens, only to realize that your actions were always meant to occur. In this scenario, the future influences the past, creating a loop where cause and effect are intertwined in a way that defies our usual understanding of time. Let's break it down with an example. Suppose you discover that a historical figure's success was crucial to shaping the world as you know it. You decide to travel back in time to ensure this person achieves their destiny. But here's the twist: your intervention was always part of the timeline. Without your actions, the event might not have happened at all. This creates a loop where the future, your decision to travel back, directly shapes the past, ensuring the timeline remains consistent. The predestination paradox challenges the idea of free will in time travel. If your actions in the past were always destined to happen, does that mean you had no real choice in the matter? Or does it suggest that your choices are part of a larger, predetermined framework? This paradox raises profound questions about fate, causality, and the nature of time itself. One of the most famous examples of this paradox comes from science fiction, where a character might go back in time to prevent a disaster, only to realize that their attempt to stop it was what caused it in the first place. This creates a closed loop where the future and past are inextricably linked, and every action is part of a self-fulfilling prophecy. The predestination paradox also ties into the idea of a fixed timeline, where events are unchangeable and any attempt to alter them only reinforces their inevitability. This contrasts with theories that suggest multiple timelines or parallel universes, where changes in the past could create alternate futures. In the predestination paradox, there's only one timeline, and every action taken by a time traveler was always meant to happen. As we continue to unravel the mysteries of time travel, the predestination paradox reminds us that the relationship between cause and effect might be far more complex than we imagine. It challenges us to rethink our assumptions about free will, destiny, and the very nature of time itself. With this paradox in mind, let's move forward to the next theory, where we'll explore yet another fascinating idea that pushes the boundaries of our understanding. Now turning to our next theory, we delve into the intriguing concept of the time-symmetric universe. This idea suggests that the fundamental laws of physics operate identically whether time moves forward or backward. In other words, the equations that govern the universe don't distinguish between past and future. They treat both directions of time as equal. This symmetry opens up fascinating possibilities for time travel and challenges our understanding of causality. Imagine a universe where every event could, in theory, unfold in reverse without violating the laws of physics. For example, if you watch a video of a ball bouncing on the ground, you wouldn't be able to tell whether the video is playing forward or backward. The motion of the ball would look equally natural in both directions. This is because the physical laws governing the ball's movement are time-symmetric. They don't inherently favor one direction of time over the other. But how does this relate to time travel? If the universe is truly time-symmetric, it could mean that traveling backward in time is just as physically plausible as moving forward. Theoretically, a time traveler could retrace their steps through time, experiencing events in reverse order without breaking any fundamental laws. This idea aligns with certain interpretations of quantum mechanics, where particles can behave in ways that seem to defy our everyday understanding of cause and effect. However, the time-symmetric universe also raises profound questions about causality. If time can flow equally in both directions, does that mean cause and effect are interchangeable? Could an effect precede its cause in a time-symmetric framework? These questions challenge the very foundation of how we perceive the relationship between events. In our everyday experience, we assume that causes always come before effects, but in a time-symmetric universe, this might not always hold true. One of the most compelling implications of this theory is its potential to resolve some of the paradoxes associated with time travel. For instance, if the universe is time-symmetric, a time traveler's actions in the past might naturally align with the existing timeline, avoiding contradictions like the grandfather paradox. This could mean that any attempt to change the past would be seamlessly integrated into the fabric of time, preserving the overall consistency of the universe. As we explore the time-symmetric universe, we're reminded that our understanding of time is still evolving. This theory invites us to consider a reality where the past, present, and future are not as distinct as they seem, and where the flow of time might be far more flexible than we've ever imagined. With this thought-provoking concept in mind, let's move forward to the next theory, where we'll uncover yet another layer of the mysteries surrounding time travel. Now turning to our next theory, we explore the fascinating quantum Zeno effect, a phenomenon that reveals how the act of observation can influence the behavior of quantum systems. Named after the ancient Greek philosopher Zeno of Elea, who proposed that motion is an illusion, this effect suggests that continuously observing a quantum system can effectively freeze its evolution. In other words, the more frequently you measure a quantum particle, the less likely it is to change its state. This counterintuitive idea challenges our understanding of how time and observation interact at the quantum level. To put it simply, imagine a radioactive atom that has a certain probability of decaying over time. If you continuously observe the atom, the quantum Zeno effect predicts that the atom will remain in its original state for much longer than it would if left unobserved. This is because each observation resets the quantum system, preventing it from evolving naturally. It's as if time itself slows down for the particle under constant scrutiny. But how does this relate to time travel? The the quantum Zeno effect opens up intriguing possibilities for manipulating time on a microscopic scale. If we can control the evolution of quantum systems through observation, could we extend this principle to larger systems or even entire objects? Some theorists speculate that this effect might one day be harnessed to create time locks, effectively freezing moments in time or slowing down processes to a near standstill. While this remains speculative, the idea of using observation to influence time is a tantalizing prospect. One potential application of the quantum Zeno effect in time travel could involve stabilizing unstable particles or systems that are critical to time travel mechanisms. For instance, if a time machine relies on quantum particles to function, continuous observation might prevent these particles from decaying or changing state, ensuring the machine operates smoothly. Additionally, this effect could provide insights into how time itself behaves at the quantum level, offering clues about the nature of time and its potential malleability. However, the quantum Zeno effect also raises profound questions about the role of consciousness and observation in shaping reality. If observation can alter the behavior of quantum systems, does this mean that our perception of time is inherently tied to how we observe the universe? Could time travel in some form depend on the act of observation itself? These questions blur the line between physics and philosophy, inviting us to rethink the relationship between time, reality, and the observer. As we delve into the quantum Zeno effect, we're reminded of the strange and wondrous nature of the quantum world. This theory not only challenges our understanding of time, but also hints at the profound ways in which observation and reality are intertwined. With this thought-provoking concept in mind, let's move forward to the next theory, where we'll uncover yet another layer of the mysteries surrounding time travel. Now turning to our next theory, we explore the intriguing concept of the Gödel universe, a solution to Einstein's equations of general relativity proposed by the brilliant mathematician and philosopher Kurt Gödel. This model presents a universe that rotates, creating conditions where time travel becomes not just possible but inevitable under certain circumstances. Gödel's work challenges our conventional understanding of time as a linear, one-way progression, suggesting instead that time could loop back on itself in a rotating cosmos. In the Gödel universe, the rotation of the entire universe generates what are known as closed timelike curves. These are paths through spacetime that loop back to their starting point, allowing an object or person to travel back in time without ever exceeding the speed of light. Imagine a cosmic merry-go-round where the very fabric of spacetime twists and turns, creating shortcuts through time itself. This idea is both fascinating and mind-bending, as it implies that time travel could be a natural consequence of the universe's structure. However, there's a catch. For the Gödel universe to allow time travel, the universe would need to be rotating at a specific rate, and there's no evidence that our universe is rotating in this way. In fact, observations of the cosmic microwave background radiation suggest that the universe is largely isotropic, meaning it looks the same in all directions with no significant rotation. This makes the Gödel universe a purely theoretical model, one that remains a thought experiment rather than a description of our actual universe. Despite its speculative nature, the Gödel universe raises profound questions about the nature of time and the structure of the cosmos. If time travel is possible in a rotating universe, what does that say about the relationship between time and space? Could there be regions of our universe or other universes where such conditions exist? Gödel's work reminds us that the laws of physics are far more flexible and mysterious than we often assume, opening doors to possibilities that defy our everyday experience. The implications of the Gödel universe also extend to our understanding of causality. If closed time-like curves exist, events could influence their own past, creating loops where cause and effect become intertwined. This challenges the very foundation of how we perceive reality, suggesting that the flow of time might not be as straightforward as it seems. While the Gödel universe remains a theoretical construct, it serves as a powerful reminder of the strange and wondrous possibilities that lie at the intersection of mathematics, physics, and philosophy. As we reflect on the Gödel universe, we're left with a sense of awe at the complexity of the cosmos and the ingenuity of human thought. This theory invites us to imagine a universe where time is not a river flowing in one direction but a vast, twisting labyrinth full of hidden paths and endless possibilities. With this thought-provoking concept in mind, let's move forward to the next theory, where we'll uncover yet another layer of the mysteries surrounding time travel. Now turning to our next theory, we delve into the fascinating concept of the black hole time machine. Black holes, those enigmatic regions of spacetime where gravity is so intense that nothing, not even light, can escape, have long captured our imagination. But what if these cosmic giants could do more than just consume matter? What if they could serve as gateways to other times or even other universes? This theory takes us to the edge of what we know about physics and challenges us to rethink the very nature of reality. At the heart of this idea is the concept of the event horizon, the point of no return around a black hole. Beyond this boundary, the gravitational pull is so strong that escape is impossible. But some theories suggest that within a black hole lies a singularity, a point where the laws of physics as we know them break down. It's here, in this realm of infinite density, that the rules of time and space might be rewritten. Some physicists propose that a black hole singularity could act as a bridge or wormhole, connecting distant points in spacetime or even different universes. Imagine falling into a black hole and emerging in another time or place. It sounds like science fiction, but the mathematics of general relativity allows for such possibilities. However, the journey would be anything but simple. The tidal forces near a black hole are so extreme that they would stretch and compress anything approaching it, a process known as spaghettification. Surviving such an ordeal would require technology far beyond our current capabilities, not to mention a way to navigate the unpredictable physics of a singularity. Even if we could overcome these challenges, there's another hurdle: the nature of time itself. Near a black hole, time slows down dramatically due to the intense gravitational field. For an outside observer, someone falling into a black hole would appear to slow down and eventually freeze at the event horizon. But for the person falling in, time would seem to pass normally. This discrepancy raises profound questions about the nature of time and how it behaves under extreme conditions. The idea of black holes as time machines also ties into the concept of closed timelike curves, similar to those we explored in the Gödel universe. If a black hole singularity could create such curves, it might allow for travel back in time. But this possibility comes with its own set of paradoxes and challenges, particularly when it comes to causality. If time travel were possible through a black hole, how would the universe prevent paradoxes like the grandfather paradox? These questions remain unanswered, but they highlight the complexity of the physics involved. Despite the many unknowns, the black hole time machine theory offers a tantalizing glimpse into the potential of these cosmic phenomena. It reminds us that black holes are not just destructive forces, but also windows into the deepest mysteries of the universe. As we continue to study these enigmatic objects, we may uncover new insights into the nature of time, space, and the very fabric of reality. With this mind-bending theory in mind, let's move forward to our next exploration, where we'll uncover yet another layer of the mysteries surrounding time travel. Now turning to our next theory, we explore the intriguing concept of the time traveler's immunity. Imagine a scenario where a time traveler moves through different eras, altering events and reshaping history. But what if the traveler themselves remained unaffected by these changes? What if they were somehow immune to the ripple effects of their own actions? This is the core idea behind the time traveler's immunity theory, a concept that could potentially resolve some of the most perplexing paradoxes in time travel. At its heart, this theory suggests that time travelers exist outside the normal flow of time, making them immune to alterations in the timeline. This means that while their actions might change the course of history for everyone else, the traveler's own existence and memories remain unchanged. Think of it as being an observer who can interact with the timeline but isn't bound by its rules. This immunity could explain how time travelers avoid paradoxes like the grandfather paradox, where altering the past could erase their own existence. If the traveler is immune, their actions wouldn't loop back to affect them, allowing them to exist independently of the timeline's changes. One way to visualize this is through the idea of a fixed point in time. Just as a rock in a river remains unmoved by the flowing water, a time traveler might remain unaffected by the shifting currents of history. This concept aligns with certain interpretations of quantum mechanics, where particles can exist in multiple states simultaneously. Similarly, a time traveler might exist in a state that's separate from the timeline they're altering, allowing them to navigate history without being constrained by its rules. But how could such immunity work in practice? Some theories propose that time travelers are protected by a kind of temporal shield, a field that isolates them from the effects of their actions. Others suggest that their immunity is a natural consequence of their ability to move through time, much like how a fish can swim through water without being swept away by the current. Whatever the mechanism, the implications are profound. If time travelers are immune to changes in the timeline, it opens up new possibilities for exploring history without fear of creating paradoxes. This theory also raises fascinating questions about free will and determinism. If a time traveler's actions don't affect their own existence, does that mean their choices are predetermined? Or does their immunity grant them a unique form of freedom, allowing them to shape history without consequences? These questions challenge our understanding of causality and the nature of time itself. The time traveler's immunity theory offers a compelling solution to some of the most puzzling aspects of time travel. It suggests that while the timeline may be fluid and ever-changing, the traveler remains a constant, untouched by the chaos they might create. As we continue to explore the mysteries of time travel, this theory reminds us that the rules of the universe may be far more flexible and far stranger than we ever imagined. With this thought-provoking theory in mind, let's move forward to our next exploration, where we'll uncover yet another layer of the mysteries surrounding time travel. Now turning to our next theory, we delve into the fascinating concept of the simulation hypothesis and its connection to time travel. What if everything we perceive as reality, our world, our history, even our sense of self, is nothing more than an incredibly advanced simulation? This idea, once the realm of science fiction, has gained traction among scientists and philosophers, and it opens up intriguing possibilities for time travel. At its core, the simulation hypothesis suggests that our universe is a digital construct created by an advanced civilization or intelligence. If this is true, then time travel might not involve bending the laws of physics as we know them, but rather manipulating the code or parameters of the simulation itself. Think of it like editing a video game. If you have access to the source code, you can rewind, fast forward, or even rewrite events. In this context, time travel becomes a matter of accessing and altering the underlying program of reality. One of the most compelling aspects of this theory is how it could resolve many of the paradoxes associated with time travel. For example, if the universe is a simulation, changes to the timeline might not create contradictions but instead be seamlessly integrated into the program. The grandfather paradox, where altering the past could erase your own existence, might simply be a glitch that the simulation corrects. This could mean that time travelers are free to explore and change history without fear of catastrophic consequences. But what does this mean for free will? If our reality is a simulation, are our choices truly our own, or are they predetermined by the code? Some argue that even within a simulation, free will could exist if the program allows for genuine decision-making. Others suggest that our sense of agency might be an illusion, with every action and outcome already scripted. This raises profound questions about the nature of consciousness and whether we are active participants in our reality or mere characters in a cosmic game. The simulation hypothesis also challenges our understanding of the nature of reality. If our universe is a simulation, then time itself might be a construct, a variable that can be manipulated or even paused. This could explain phenomena like déjà vu or precognition, where people feel as though they've experienced moments before they happen. It might also provide a framework for understanding how time travelers could exist outside the normal flow of time, as we explored in the previous theory. As we consider the implications of this theory, it's clear that the simulation hypothesis offers a radical new perspective on time travel. It suggests that the barriers we perceive, like the laws of physics or the linear nature of time, might be nothing more than the rules of a program, rules that could potentially be rewritten. Whether or not our universe is a simulation, this theory invites us to rethink the boundaries of possibility and imagine a reality where time travel is not just a dream but a feature of the code. With this mind-bending theory in mind, let's move forward to our next exploration, where we'll uncover yet another layer of the mysteries surrounding time travel. Now turning to our next theory, we explore the intriguing concept of cosmic strings and their potential role in time travel. Cosmic strings are hypothetical one-dimensional defects in spacetime, remnants of the early universe that could stretch across vast distances. Imagine them as incredibly thin, incredibly dense threads, thinner than an atom but with the mass of a mountain. These cosmic strings, if they exist, could hold the key to bending spacetime in ways that allow for closed time-like curves, loops in time that could theoretically enable time travel. The idea of cosmic strings stems from theories about the early universe, where rapid phase transitions during the Big Bang might have left behind these strange, thread-like structures. Unlike black holes or wormholes, cosmic strings don't rely on massive gravitational fields or exotic matter. Instead, their unique properties come from their extreme density and the way they warp spacetime around them. If two cosmic strings were to move past each other at high speeds, they could create a region of spacetime so twisted that it forms a closed loop, a closed time-like curve. This loop would allow an object or even a person to travel back in time, returning to the same point in spacetime from which they began. One of the most fascinating aspects of cosmic strings is how they sidestep some of the challenges posed by other time travel theories. For example, unlike wormholes, which require exotic matter to remain stable, cosmic strings rely on their inherent properties to create spacetime distortions. This makes them a more plausible candidate for time travel, at least in theory. However, detecting cosmic strings is no easy task. They are incredibly elusive, and their effects on spacetime are so subtle that they have yet to be observed directly. Scientists continue to search for evidence of these cosmic threads, using everything from gravitational wave detectors to observations of distant galaxies. But what would time travel via cosmic strings look like? Picture this. A spacecraft approaches a pair of cosmic strings moving at near light speeds. As it enters the twisted region of spacetime created by their interaction, the spacecraft is caught in a loop traveling back in time. The journey would be instantaneous from the perspective of the traveler, but from the outside, it might appear as though the spacecraft vanished and reappeared at an earlier moment. This raises questions about causality and the potential for paradoxes, but as we've seen in previous theories, the universe might have ways of resolving such contradictions. The concept of cosmic strings also ties into broader questions about the nature of spacetime and the universe itself. If these strings exist, they could provide clues about the conditions of the early universe and the fundamental forces that shaped it. They might even offer a glimpse into the underlying structure of reality, hinting at a deeper connection between time, space, and the fabric of existence. As we consider the possibilities of cosmic strings, it's clear that they represent another fascinating avenue for exploring the mysteries of time travel. While they remain theoretical for now, their potential to unlock the secrets of spacetime continues to inspire scientists and dreamers alike. With this theory in mind, let's move forward to our final exploration, where we'll delve into the role of consciousness in time and how it might shape our understanding of this enigmatic phenomenon. Now turning to our final theory, we delve into the enigmatic relationship between consciousness and time. What if our perception of time isn't just a passive experience but an active force that shapes reality itself? This theory suggests that consciousness might play a fundamental role in how we perceive and even manipulate time, bridging the gap between quantum mechanics and philosophy. At the heart of this idea is the notion that time, as we experience it, isn't an absolute, unchanging entity. Instead, it's deeply intertwined with our awareness. Think about how time seems to fly when you're engrossed in an activity or drags on when you're bored. These subjective experiences hint at the possibility that consciousness influences our perception of time. But could it go further? Could consciousness actually alter the flow of time itself? Quantum mechanics offers some intriguing clues. In the quantum world, particles exist in a state of superposition, meaning they can be in multiple states at once until observed. The act of observation, essentially, the intervention of consciousness, collapses these possibilities into a single reality. This has led some scientists and philosophers to speculate that consciousness might not just observe reality but actively participate in shaping it. If consciousness can influence the quantum realm, could it also affect the fabric of time? One compelling theory is that consciousness operates outside the linear flow of time. Imagine time as a river flowing from the past to the future. Consciousness, in this view, is like a boat that can navigate upstream or downstream, allowing us to access memories of the past or anticipate future events. This idea aligns with the concept of precognition, where individuals claim to have glimpses of future events. While such phenomena remain controversial, they raise fascinating questions about the nature of time and the limits of human perception. Philosophers have long debated the nature of time and consciousness. Some argue that time is an illusion, a construct created by our minds to make sense of the world. Others suggest that consciousness exists in a timeless state, with our perception of time being a byproduct of how our brains process information. These ideas challenge the traditional view of time as a fixed, linear progression and open the door to the possibility that consciousness could one day allow us to transcend its boundaries. The intersection of consciousness and time also touches on the concept of free will. If consciousness can influence time, does that mean we have the power to change the past or shape the future? This idea echoes the predestination paradox we explored earlier, where actions taken by a time traveler were always meant to happen. But if consciousness is the key, perhaps it offers a way to navigate these paradoxes, creating new possibilities without disrupting the fabric of reality. As we conclude our journey through these 25 mind-bending theories, it's clear that time travel is more than just a scientific curiosity. It's a profound exploration of the nature of reality itself. From the grandfather paradox to cosmic strings, and now to the role of consciousness, each theory challenges our understanding of time and invites us to imagine a universe far more complex and mysterious than we ever thought possible. So, what's your favorite theory? Let us know in the comments below, and don't forget to subscribe for more deep dives into the mysteries of the cosmos. Until next time, keep exploring the unknown. Now turning to our final thoughts, let's take a moment to reflect on the incredible journey we've just taken through 25 mind-bending theories about time travel. From the classic grandfather paradox to the mysterious role of consciousness, each theory has pushed the boundaries of our understanding, challenging us to rethink the very nature of time and reality. These ideas don't just belong to the realm of science fiction. They're grounded in cutting-edge physics, philosophy, and even quantum mechanics, offering glimpses into a universe far more complex and fascinating than we ever imagined. We've explored how time might not be the linear, unchanging force we once thought it was. Theories like the many worlds interpretation and the block universe suggest that past, present, and future could all exist simultaneously, while concepts like wormholes and closed timelike curves hint at the possibility of bending spacetime itself. We've grappled with paradoxes from the Bootstrap Paradox to the predestination paradox, and pondered whether free will can coexist with the idea of time travel. And we've even ventured into the realm of consciousness, asking whether our minds might hold the key to unlocking the mysteries of time. Each theory invites us to question what we think we know about reality. Could time travel one day become a reality, or are the laws of physics destined to prevent it? Are we living in a multiverse where every decision creates a new timeline? Or is the universe a single, unchanging block where everything has already happened? These questions don't just challenge scientists, they challenge all of us to think bigger, to imagine a universe where the impossible might just be possible. So, what's your favorite theory? Do you find the idea of parallel universes thrilling, or are you captivated by the thought of consciousness shaping time itself? Let us know in the comments below. We'd love to hear your thoughts. And if you've enjoyed this deep dive into the mysteries of time travel, don't forget to hit that subscribe button and ring the notification bell so you never miss another exploration of the cosmos. Until next time, keep questioning, keep imagining, and keep exploring the unknown. The universe is full of secrets waiting to be uncovered, and who knows, maybe one day you'll be the one to crack the code of time itself.